Okay, we're going to be looking at extreme values again, but in this case, we're not going to be looking really for absolute extrema because we don't have a closed interval for this function. So we're going to be talking about what's called local extrema. And let me write that down. Local extrema. And what does that mean? That means that we're looking for a max or a min in a neighborhood of a function. Okay. Now, technically speaking, you could have absolute value, an absolute, not absolute value, suppose, but an absolute extrema, but not necessarily. Okay. So what we're going to do is we're going to look at this graphic real quick. And if you notice here, the absolute minimum, all right, is found at this value of x equals a because that is actually the lowest point on the graph. So absolutely it's the lowest point. Okay, and now notice that this function is defined on the interval from a to b only. Okay, then we have what's called a local minimum, because if you see in the neighborhood, like suppose in between c and d, well, E, the point E, is the lowest value. Okay, so that's right, locally, it's a minimum value. And then we, of course, get to the discussion of absolute maximum. This is absolutely the highest point on the graph. But then you have also what's called local maximum. All right, and that is that in the neighborhood, like in this case from A to E, this point C right there is the highest value. So you have local max, you have local mins, all right? But we're not going to be considering in the examples we're going to work on the absolute values or absolute extrema in this case. We're going to only be looking at locally defined extrema. Okay, and we're going to do that with what's called the first derivative test. Now, the first derivative test has us analyze the behavior of the function, okay, in terms of its derivative. So what we're going to do is we're going to first find the derivative, and I know it says y, but I just prefer function notation f of x. So let's say f prime of x, because we're going to have to probably plug in something. So let's take a look here. So f prime of x equals 2x plus 2. Okay, so we're going to take that derivative, 2x plus 2, and we're going to set it equal to 0. And we get 2x equals negative 2. And then x, of course, will equal negative 1 when you divide both sides by 2. Okay, so we're going to be investigating the function around the point x equals negative 1. So what I'm going to do is I'm going to draw a graph, and let me actually switch the color of the graph. Let's make it blue. Here's this right here. I'm going to notate my number negative 1. I'm going to write off here to the side f prime of x, and this graph I'm going to give a name, and let me write it in a different color. I call it the wiggle graph. Now, I read it in a book somewhere and the name just stuck, so I just mention it every year, the wiggle graph. Okay, so what we're going to do is we're going to take a look at how this function behaves before and after negative 1. And all you do is you pick values before and after negative 1 and you plug them into f prime, the derivative. So if you pick a number after negative 1, suppose like 0 would work. 2 times 0 plus 2 is a positive 2. So we really don't care what it evaluates to. We just want to know that it's positive. If you pick a number before negative 1, like negative 2, or negative 2 works. 2 times negative 2 is negative 4 plus 2, negative 2. So we really don't care again what it is, just the fact that it's negative. Well, I need you to understand something. If the derivative goes from negative to positive, all right, if it goes from negative to positive, we actually call that a minimum. We call that a minimum. Okay, why? Because the derivative the tangents, suppose, are negative, and then they go to positive. Well, if it goes from negative to positive, and this right here is 0, think about it. That's a minimum value. Okay? I call this one the pit bull of calculus. Why? Because it goes from negative to positive. If you know any pit bull songs, you'll know what I'm talking about. All right? So now, let's erase this little graph there. What we're going to do is we're going to evaluate the original function f of x at -1 to get the point of this critical value, of this extrema, this minimum, if you will. All right, so f of -1, I'm going to plug in -1 into the original, and let's see what I get. Okay, so I plug that in. You can work it out on your calculator if you want to. I get -4. So I have a local minimum, a local min at the point -1, -4. Now, coincidentally, because this is a parabola, and this right here is actually the vertex of the parabola, if you will, it's actually also an absolute minimum. But we're considering that we would only have absolute extrema on closed intervals, so we'll call it a local min here. All right, so we'll jot that down right there. Now let's take a look at the next problem. Move it, scoot it up just a little bit. All right, so again, we're going to follow the same process. Again, I'm going to call this f of x, and I'm going to take the derivative and find f prime. And what do I get? 3x squared minus 6x, and the derivative of 1 is 0. So I'm going to do some greatest common factor factoring. 3x times x minus 2 is what I get there. I, of course, set this equal to 0. And what do I get? I get, in the first case, 3x equals 0, so x equals 0, and x minus 2 equals 0, so x equals 2. And so these are the points that I'm going to plot on my wiggle graph. And let me make that blue again. There we go. So again, I'm going to notate by putting f prime of x. This tells me where I'm plugging in my test points, if you will. I'm going to put 2 little marks here for 0 and for 2. And again, let me write down the fact that I call this the wiggle graph. All right. Okay. So if I pick some value before 0, suppose like -1, I plug it in here and here for x. What do I get? Well, you plug in a number like -1, for example, you're going to get a positive number. Okay, so 3 times -1, -3, -1 minus 2, -3, -3 times -3, positive 9, for example. So that's positive. Then you pick a number like 1. So 1 would be right in here. Okay, 3 times 1 is 3. 1 minus 2 is -1. So that's what? 3 times -1, -3. So again, we really don't care what it evaluates to, just the sign. Then you pick a number after 2. Suppose 3. 3 would work. You plug in there, you get 9. 3 times 3 is 9. 3 minus 2 is 1. And that's 9 times 1 is positive 9. So again, we don't care what it evaluates to, just the sign of the number. All right, so positive, negative, positive. Well, notice what happens if it goes from positive to negative. So the derivative, the tangents are positive, and then they become negative. That's what we call a maximum. So right here, we have a maximum. And then the tangents go from negative to positive. So that right there is a minimum. So minimum here. All right. So again, we evaluate our function at those values. So I'm going to find f of 0. So that's 0 cubed minus 3 times 0 squared plus 1. And f of 2, that's 2 cubed minus 3 times 2 squared plus 1. What does that look like? This is 0. I'm sorry, no, this is 1. My mistake. Or as the kids say these days, my bad. All right. Well, maybe they're not. Those aren't the kids these days. But anyway, then the next one we get here, 2 cubed is 8 minus 3 times 2 square, which 2 squared is 4 times 3 is 12. 8 minus 12, negative 4 plus 1, negative 3. And so we have our points here. And that is to say that we have a local, and let's see here. We have a local max at 0, negative 1. I'm sorry, 0, positive 1. And a local min at 2, negative 3. And so there are our answers. Okay, but just remember, if the derivative goes from positive to negative, it's a maximum. And if it goes from negative to positive, it's a minimum. Again, I call this one the pit bull of calculus. And I think if you go back and listen to that Pitbull song, you know which one I'm talking about. Pitbull's the only guy that can rhyme Kodak with Kodak, by the way. I mean, yeah. So go back, watch that video. Shameless plug there for Pitbull. But hopefully this makes sense. And the wiggle graph concept, I think, is really helpful in determining local extrema anyway. And it's fairly easy to do. So again, I hope this video was helpful. And remember, like and subscribe.